Good morning, everyone. I'm going to share with you the 3 papers I chose for visualization research today. Okay. So when I chose these papers, I didn't have a central unifying theme in mind, so I'll just share with you my motivation for each of them. I guess maybe an overall theme would be practicality. I was looking for things that I could apply to my work. So the first one, this visualizations as sanity checks paper. This process of checking your data through visual exploration is kind of a primary function of visualizations. So this seemed like something we could all use and apply to be very practical to learn about. The paper about externalizing implicit error. Also, communicating error about your data is really important and also can be challenging. So this kind of resonated with me as I'm trying to figure out how to do that with my own research. And in particular, the research assistantship I'm on, the APHIS Pathways project, has a lot of these same challenges where the experts know about the data inconsistencies, and as a matter of fact, they don't trust the research that has been done previously because of the, not acknowledging those inconsistencies. So we need to figure out a way to handle that. And then the last one, the trade network analysis paper. This is a personal interest of mine, global food security, and in particular how those global supply chains can affect local communities and have implications for local food systems. And also this is relevant for my research as well as the Pathways project is trade network analysis. So the first paper, the visualizations as sanity checks. This was written by, the first author is a research scientist at Tableau, just a disclaimer, I guess. The other co-authors were academic researchers, and I thought this was pretty interesting. This paper was part of a bigger project called the Black Hat Visualization, which investigates if you can maliciously hide important information to mislead people about visualization. So it seems like just a bigger topic that is relevant and interesting to us all. So the motivations for this paper, again, visualizations are important for exploratory data analysis, in particular when understanding issues around data quality. But design parameters can obscure these flaws. The author gave this catch-22. You can't trust the visualization if you can't trust the data, but you can't trust the data if we can't visualize it. So some context for the paper. It focused on univariate distributions for several reasons. One in particular was just simplicity for this particular approach. And they chose 3 different distribution plotting methods. Histograms, where the number of bends or the number of discrete categories for the data is the parameter of interest. And the default way of choosing these bends is assumes a normal distribution in many of the visualization softwares, which is not always the case, as we know. And then second is density plots. Kernel bandwidth is the parameter of interest for these. Again, the default rule of thumb assumes a normal distribution for these. And then dot plots, which is just a single point representing each data point along one dimension. So these are one-dimensional distribution plots. The issue with these is overplotting or obscuring data because of data being plotted on top of each other. Strategies for this are to jitter points or just offset the points in the y direction or change opacity of the points. And the opacity is the parameter that they're looking at. The problem with these is that there's no data-driven optimization of opacity settings now. They also use this framework of algebraic visualizations with 2 principles. There should be a difference in a data visualization only when the data is different, and there should be similarities in visualizations only when the data is similar. So these give 2 examples of these issues. The hallucinator, we have 2 sets of data that are exactly the same, but the plotting order causes them to look very different. In the confuser, we have 2 visualizations that look exactly the same, but because there's no color encoding for the data series, you can't tell that they're actually very, very different. So the left is actually straight lines, and the right plot is 2 lines connected at that center vertex. These are called confusers. They also framed this around adversarial visualization, so the idea that you can obscure flaws by adjusting the parameters. So on the left, I show data distributions. The leftmost is without flaws, and the right is with flaws. And all of these plots have been designed to obscure those flaws, whereas on the right set of plots, we have the same thing going on, but the parameters have been adjusted to highlight the flaws. So this is an example of what they call adversarial visualizations. So the researchers wanted to look at if data flaws have some characteristic visual patterns, and if those patterns are robustly detectable across visualization design parameters. Or in other words, can you detect these flaws equally across visualizations and parameter settings? So they used a lineup protocol, which basically presents the participant with a set of data visualizations that are all random samples from the same distribution, with one of them having some added flaws. And then it asks the participants to pick out which one of the visualizations has the flaw. They tested 3 flaw types: gaps, outliers, and spikes, and 3 chart types: histograms, density plots, and dot plots. And they also looked at 3 parameter settings and 3 flaw magnitudes. They used an online crowdsourcing platform to gather 32 participants. So the results, overall for detecting flaws, they had about 50% accuracy across all of the things they tested. The easiest to detect were spikes in data. Middle was outliers, and the hardest to detect were gaps. And also, the higher the magnitude of the flaw, the easier it was to detect, except in the case of outliers. So the density plots performed the best as far as people being able to accurately identify the flaws. Then dot plots and then histograms were the worst performing. But this was kind of overall their performance. Depending on those flaw types, this actually varied a little bit and there wasn't a significant differences in all cases. So the parameter setting results, I just used this graph. There's a lot of variability in the way parameter settings affected the results, but I'll just point out with the bottom set of charts, they're looking at spike detection. We have density plots compared to histograms compared to dot plots. And within those, you're comparing the parameter settings, or magnitude of the parameter settings. And overall, it seems like the more conservative choices for those parameter settings had the lowest accuracy for flaw detection. So, for example, histogram, if you use fewer bends, it was more difficult to detect spikes. But overall, the parameter settings kind of had variable effects. And for the specific chart types, the density plots performed really robustly across all conditions. But in particular, detecting gaps was sensitive to over-smoothing, or the kernel size, bandwidth size. However, detecting outliers, you can actually benefit from a higher smoothing. So there's some different considerations when you're thinking about kernel bandwidth, depending on the flaws you're looking for with density plots. Histograms, as I mentioned, had low performance overall. They were terrible for gap detection, and aggregating the data into discrete bends can obscure data patterns, flaw patterns. Dot plots performed well, and you could use a wide range of opacity settings as long as you're dealing with the overplotting issue. So as long as you use some amount of, or lower the opacity to some degree so that you could see data being plotted on top of each other, a wide range of those settings is effective. So overall, this study showed that it's important to know what the default parameter settings are for visualizations and consider how you maybe should change them if you're looking for flaws. They also suggested that we could integrate automated anomaly detection and actually provide the user with a warning, prompt them that maybe they need to look deeper. They also suggested that ensemble visualizations might be a good idea to provide as a default. So just several different ways of looking at the same data juxtaposed. And also we need to be thinking about defensive visualization design. This is pretty interesting. I'm not really sure what that means, but they design that is more robust against the strategy of obscuring flaws. So they provided a GitHub site. For the sake of time, I'm not going to bring it up, but they have some interesting tools there, just documentation, but then also a tool where you can actually generate some data, visualize with these different plots, and then add flaws and see how the parameter settings actually affect them. So moving on to the framework for externalizing implicit error. This was done by a group of academic researchers. And the motivation for this is basically garbage in, garbage out. So visualizations are only as good as the data they consume. And it's well known that often experts will interpret visualizations by adjusting the data contextually based on their knowledge about data inconsistencies. And that knowledge is not accessible to others. They call this internalized implicit error. So like I said, I was excited about this paper because of the motivation and how useful it could be for my research. But after I started reading it, I felt like this. It has a huge emphasis on qualitative research design, and they kind of explained ad nauseum their process. But despite that, I'll do my best to present what they showed. So first, what is implicit error? This is error that originates from measurement and data generation. It's usually systematic, and it's not explicitly recorded anywhere. So it's known by the experts with lots of experience, but it's generally qualitative. How is it handled at this point? One is standardized data generation, so try to eliminate or minimize it at its source. And then also a lot of times people use simulation models that will generate synthetic data to simulate the process they're interested in versus the raw collected data. Also, we rely on users to being able to juxtapose their visualization with their contextual knowledge. We also have some methods for handling quantifiable error, but in most cases this is qualitative, so we don't have good ways of handling it. So this research wanted to fill some of these gaps. These implicit errors still persist despite efforts to handle them while entering data collection. And we need methods to be able to transfer knowledge about these errors between users and also amongst experts to standardize interpretations of data. Another important thing was that these errors have the same effect as quantitative errors, but since they're qualitative, they require different approaches for handling them. So this research proposes a framework of how to understand and deal with implicit error, and then also provided a detailed summary about their research design process. And their motivation for doing this, by the way, was repeatability. So we talk about open science a lot, so this was their motivation. So it's a good motivation, but it's kind of difficult to read. So I broke this into 3 phases. The first was their original intent, which was to design a decision support tool to be used by USAID to track Zika. So the way they approached this was to interview experts, understand the domain, use a process called reflective transcribing. And they also did rapid prototyping. So they prototyped the tool early on and then presented it to their experts or their domain experts to get feedback. And so they used this iterative process to abstract tasks and the data. So the tasks they identified were to track Zika over time and space, figure out how it's impacting the local population, and then determine if the current response is appropriate. But at this point, when they started showing these prototypes to the experts, they started getting feedback like, I have to suspend my disbelief about the data in order to look at this visualization. And they just highlighted all these issues, and basically the usefulness of the visualizations was limited because of that. So the researchers kind of pivoted here and decided to add this extra objective of addressing this implicit error. The next two phases, phase 2 was about understanding the error in the Zika data. Again, they did this rapid prototyping where they added an annotation feature. So users could drop a pin and add some annotation about the error they know about that data in that geographic location, or an annotation message board. And so they used this process to collect information about the errors. And in the final phase, they analyzed these data discrepancies and categorized them and basically boiled them down to what are the characteristics of the error. So here we're getting into their results. They provided a definition of implicit error and listed all the things that we need to define about that error in order to start to kind of quantify it. So we have all of these characteristics about the type of error, the direction. So is the error causing over-reporting or under-reporting? How big is the error? How confident are you? But then also they said it was important to have a contextual description, just to give people the full story of what's going on. So they used this idea of a DIKW pyramid, which is basically just that data is transformed into information, is transformed into knowledge, and then into wisdom. And they said that if we just flip that pyramid upside down, we can model the process for error externalization. So experts have this wisdom, they transfer it into knowledge, into information, and then it's codified into data. And they use a knowledge-assisted visual analytics and added the concept of information. Again, this is all very abstract. But the idea is basically these diagrams are showing how on the left, when you start to look at the data visualizations without that piece of information about the errors, you're limited to these components. You're limited to your perception, your current knowledge, your ability to explore the data, and then the visualization itself. But when you can start to externalize your knowledge and then add that as a component of information into the visualization, then we can start to use that information as data in your interpretation. So here is the system that they developed. Basically, you can click on anywhere in the map and it'll pull up this dialogue where it's basically like a questionnaire about the error, where it asks you to define all those characteristics that we talked about. And then in the actual visualization, it will encode some of these characteristics with color so that you can start to kind of get an idea of the overall trends. You select a radio button here at the top to identify which particular aspect of the discrepancy you're interested in. So here we have pipeline selected, and the different colors represent where in the data pipeline is the error introduced. Basically, yeah, they're just trying to move towards quantifying the error and providing it side by side with the visualization. They don't actually change the data at all, they just give you extra information about the data. And also, this was one of their research goals to document their process. So they provided a website with this timeline. I'm not going to bring it up for the sake of time, but it's interactive. You can filter down to a certain time frame to look at exactly what they did in their research process. You can hover over these data points to get a little description or notes about what they were doing during that process. So this was their way of documenting what they did. So overall, this research formalized the definition and notion of implicit error, and it provided a framework to transfer knowledge about that implicit error. They think that this is the first step for modeling this kind of error, hopefully to do some mitigation in the future. And they even think that they could possibly model how experts adjust their interpretation of visualizations based on this error knowledge and simulate that adjustment and actually modify the data for users. So my final paper about spatiotemporal trade network analysis. This was done by a group of academic researchers as well as one researcher from GE Global Research, and it was partly funded by the Department of Homeland Security. So the motivation for this research is that the relationship between countries in supply chains is very complex. There are a lot of interdependencies, and in particular, there's a lot of transferring of risk. So for example, if a country has some sort of natural disaster, some climate situation where they can't produce as much food as they normally do, and they're an exporter of some food, they would withhold whatever they need and then just export less. So that would affect all the countries that import from them generally, and it would raise prices. So in particular, those countries that can't afford the higher prices would have an issue with food shortage. So overall, this is a threat to global food security. And interestingly, they were trying to correlate this with political instability. So is this kind of dynamic a driver of political instability? So why use visual analysis? As we all know, spatiotemporal data has overplotting issues, issues with occlusion. So having some sort of dynamic visual way of analyzing this type of data is important. Just because of the sheer size of this kind of data, you really need to be able to cluster it, filter it, explore it, and also automatically detect anomalies to direct where you want to look. So other research, they say they're using a different approach than other research. Other people looking at trade analysis like this have used flow maps. And they say that for their purposes, flow maps aren't really necessary. They can be too complex and require some bundling of flow pathways, and core clef maps are actually adequate for them. Other vulnerability analyses have just looked at regions or subregions and haven't considered that network effect or transfer of risk. And also, they're not interested in geography, really. They're not interested in regions. They're more interested in topology, or how countries are connected. So they put together a framework to explore trade network topology and how that correlates to political instability, and then identify countries that might have similar patterns in trade, and then investigate how the transfer of risk is happening within the food supply chain. So they used several different data sets, some agricultural trade data from the UN, two metrics of political stability, and then GDP from the World Bank. They identified some tasks. They wanted to be able to guide their users to anomalies, tell them where to start exploring the data, and then find countries that have some sort of similar anomaly or some maybe response to that anomaly, and then be able to inspect how the trade patterns are similar or different between those countries. And then inspect how those anomalies might spread throughout the supply chain. So a couple of concepts that are important for how they approach this. Triads, which is basically 3 connected nodes. Each node represents a country. And there are 13 possible combinations of the relationship between those 3 nodes. So in this example, we have Thailand. Thailand would be the top node in all of these triads. And in scenario 1, Thailand is exporting to 2 countries, indicated by the arrow. And then here, in node or triad configuration 3, Thailand has 12 situations where it's exporting to one country, and that country is then exporting to someone else. So this kind of trade pattern analysis boils down all the different relationships that are out there for trade. And then you can actually compare countries. So we have a vector of the frequency that country has that type of triad structure compared to, so in this case we have Thailand compared to South Korea. So you can see that just based on visual comparison, South Korea has a lot more relationships in the 9 to 13 range, which are mostly importing scenarios. So we can see that South Korea tends to be more of an importer compared to Thailand. Another concept is dependency and leverage. This is basically just how much of a country's imports are coming from one particular country. So we have the example of China. It is highly dependent on US and Australia and France. A lot of its total imports come from these particular countries, so it's highly dependent on them. Versus leverage, China has leverage over Russia, Mongolia, Australia, et cetera, because it's exporting a lot of products to them. So they put together this visualization framework that's made of 5 components, and I will go through each of them. The first is this country product matrix. The function of this is to help the user identify places where they should look further. So the matrix shows countries on one axis and then products on the other. And the degree of, or the darkness of the gray indicates the correlation, the number of correlations between that product, country's products like export and import activities, and their political stability over time. So you can choose to look at a set of country and commodities, and then it'll open up a more detailed view where you can look specifically at what activities are correlated with political instability. And here's an overall view of the framework. At the top, we have a timeline where you can visualize whatever metric you're interested in, and where you have sudden drops or rises, it will automatically detect an anomaly there. You can click on that point, and that will open up the rest of these kind of widgets. First is the choropleth map, which will, based on whatever you're interested in looking at. So here we're looking at rice, the quantity of exports. So this is showing where Thailand is exporting rice. And then it'll open up these mini maps where there's kind of the opposite thing going on. Where are countries being affected by importing rice from Thailand? And then it will show the correlation of these events with political instability over time. And then down here, it will do a clustering function. You can choose to cluster the countries that are involved in this anomaly by different characterizations, in particular by triad. So if we cluster countries that have similar triad structure that are involved in this anomaly, the idea is that it will maybe highlight some countries that would be affected in similar ways. And then over on the right, we have a diffusion graph, which shows how the activities in Thailand could affect other countries. Countries that are closer to Thailand in this graph are more directly affected, and the farther away, they might be indirectly affected. So, overall, they provided a framework for identifying temporal anomalies and trade features, and then correlated those anomalies with political stability measures. They integrated triad analysis to provide some novel insights into these processes. One problem is that a lot of anomalies are detected, so they need a better way of figuring out which anomalies are spurious and which ones you should actually look at. They also decided choropleth maps are limited just because of the sheer number of countries that you need to visualize with each map. A couple of critiques from me that this has really coarse temporal resolution. We're just looking at one data point per year. And also, it doesn't provide any scenario testing. So it seems like that would be a major functionality for this, maybe in the future.